I'm Tobias Kuna. I'm from the University of L'Aquila and I work in probability and mathematical physics.
My name is Jeroen Wouters. I'm a lecturer here at the University of Reading in the Mathematics and Statistics department, and I work on rare event simulation methods and model reduction.
And my name is Jochen Broecker. I am an associate professor here at the University of Reading, with a split position between the Department of Mathematics and Statistics on the one hand and the Department of Meteorology on the other hand. And I work on data simulation and also on forecast verification, or more generally on all kinds of problems related to data in the context of environmental sciences.
And I'm G Carigi. I'm a postdoc at the University of L'Aquila in Italy and an alumni of the University of Reading. And I do mathematics for geophysical fluid dynamics.
So in our program we had participants coming from a number of different backgrounds. We have mathematicians, we had meteorologists and people also working on the more practical aspects of meteorology. So two themes that bring those people together is first a search for simplified models for the fluid flows that drive the weather and the climate. So from a mathematical point of view, you may want to prove certain properties of these equations, but the full 3D Navier-Stokes equations may be too difficult to say something about. So there, mathematicians are also interested in looking for perhaps special cases where you can say more about these solutions. But this also is a theme that practitioners are very much interested in, because they need to numerically solve the flow of the atmosphere, for example, to predict the weather or to run climate models. And these atmospheric flows and oceanic flows, they are much too complicated to solve completely numerically. There's a large range of time scales involved. There's a large range of spatial scales involved. There are interactions between different components of the climate system. So there also a search for simplified models that can be run efficiently on computers is a very important theme. And then a second theme that that bring these two together that I can think of is a search or an interest in statistics of these statistical properties of these systems. So also from a mathematical point of view, maybe you can say something about statistical properties, even if you can't say anything about a particular solution of the system. But also from a practical point of view, someone predicting the climate is not interested in the weather on the 25th of March of 2110. They are more interested in the statistics of the climate system. So this is also one theme that brings these two communities together.
On the other hand, you have people who are interested in the weather, and on our workshop we have people, or on the program we have people who are doing this from a mathematical side, from an environmental physics side, and also from an operational side. Operational here means they actually do make forecasts on a daily basis, and these people are interested in reconstructing the current state of the weather, given all the data that we have, like satellite data, measurement data, and so on, and they need to fold that into the model in order to generate a prediction of how the weather might be like in the future. So you reconstruct the weather of today with the help of the model, with the help of your knowledge of the dynamics, and then you can use that in conjunction with the model to produce forecasts of the, let's say, next 10 days or so. And this process is called data assimilation, and it is very important, as I said already, in operations, but also raises very, very difficult and very interesting mathematical problems. And this was also a major theme of this program.
Yeah, and we thought that the kind of satellite program of the Isaac Newton Institute would be ideal to bring this kind of people together, in particular because in Reading we have also some track record of this. That I mean, besides the very strong meteorology department which we have in Reading and other institutions like the ECMWF, which are working on this kind of problems from an application side, we also have a longer-standing center which of mathematics of planet Earth hosted at our university, and as the others described, somehow there are somehow very different cultures coming together, and so the program gave us a framework in which there was a longer time period so that we can really somehow try to understand each other's problems and also adapt to each other's language, which is maybe more difficult than sometimes it seems at a first glance.
Well, from a mathematical perspective, for sure this is a topic that allows the application and the use of even more sophisticated and very sophisticated mathematical techniques. I don't know, I'm thinking of optimal transport at the moment, or something more related to ergodic theory that had strong developments in the last years, to applications that we will see on our skin every day, or almost not, for the weather, for understanding the weather and the statistical properties of it in terms of the climate. So this is a very exciting theme, I would say, also and especially from a mathematical perspective, but also for the practitioners, because this is something that they're doing on the everyday basis, and that a deeper understanding of the physics and the mechanisms behind weather or atmosphere and ocean dynamic is crucial for our understanding. Any addition to this?
Yes, so I mean, very personally, I think that we see a lot of developments recently in big data and
as well.
Data science and so on is a hot topic, so to speak. But I think what is lacking there, or what I find lacking there, is making a link with dynamical problems that you see in the atmosphere and the ocean. And this is something I'm personally very interested in, and doing statistics for time series, for instance, that have strong correlation, which coming from the underlying dynamics, underlying physics. This is something that I just find very interesting.
I find it's also very, very rewarding somehow to have some closer contact with people who are more practitioners or work in the practice. They sometimes give you, I mean, new ways, or ask you new questions you actually never thought about, which are natural from their point of view, but and that somehow, because we choose the topic in this way, maybe in this case also one can actually contribute something as a mathematician, using the tools we have, but in a very different way than they were envisioned at the beginning.
So from a scientific perspective, I would say that finding a common language between these two communities that we've been describing so far, it was one of the biggest challenges that we had. So finding the common ground and really maybe the same level for the same thing, that sometimes can be described with different terms. But having the opportunity, especially during the residential program, to have like these 2 weeks of seminars and time that you can spend together, maybe in the same offices, or what's the time really to describe what is your problem to your colleagues, that gave so much opportunity to lay that ground of understanding between the two communities. So yeah.
Not another thing on a more practical level is being the first, or one of the first satellite programs of the Isaac Newton Institute. We had some things that we needed to take care of that maybe wouldn't be necessary using the infrastructure from the INI. So, for example, we had to book accommodation and catering and so on. But there we had fantastic support from the Isaac Newton Institute, both from their staff, and also we had funds to get administrative support here, or to pay for administrative support here in Reading, and this was really very helpful.
Yeah, but also another advantage of being at Reading is having also somehow kind of this metrology-related institutions really somehow also allowed to attract practitioners which maybe would have not come to something which wouldn't have been in Reading, because this is somehow just already a natural attracting point for them, and so.
And then maybe it's more advertised to mathematicians, and so this will get on their radar.
Exactly.
Being here. So from perspective of early career researchers in particular, I think a program like this, it's a great opportunity for creating a network. So to really be exposed more to people more senior than you in the scientific career, but also your peers, and try to create a network of scientists with which you can work maybe during your PhD, but more importantly after your PhD and during your early years of your career. So I think there's going to be connections that's going to be career-long born in here, and especially after the pandemic, where so few students had the opportunity to travel and to meet other people in person. I think this has a very big impact on their future career. You surely have in mind.
Yeah, I also want to mention that we really had a very wide field of participants. Just want to mention two very concrete applications that were discussed. One was in bio or marine biology, biochemistry, on the data simulation of chlorophyll in the ocean. And then there was also one application on flight patterns of aviation flight patterns, to very direct applications of our workshop.
And we also had presentations from colleagues in the Met Office, for instance, without any scientific results, but rather lining out to us how they plan to set up their system in the future. What are their plans to how their model and the data simulation will look like, in order that mathematicians and physicists can see what potential problems might come up with that system in the future. So thereby kind of inviting people to take an interest in this and maybe even anticipate problems that might come up in the context of this system in the future.
Yeah, and I mean, I had one young researcher coming to me and just saying, I mean, he just saw how cool science actually can be, seeing all this kind of what you can do with math.